Electromagnetic induction. Here are the questions given on quiz number 9. First one, a generator produces 60 amperes of current at 120 volt. The voltage is stepped up to 4500 by a transformer and transmitted through a power line of total resistance 1 ohm. Find the percentage power lost in the transmission line if the voltage is not stepped up. Now understand that the primary use of a transformer is to increase the voltage and thereby decreasing the current. And when you transmit a voltage, a high voltage at low current, the heat produced in the transmission wires would be less. And that is the reason why voltage is stepped up, thereby the current goes down. So this problem just illustrates that very important function of a transformer. Okay, without stepping up, if this had been transmitted at 60 amperes and 120 volt, then the power lost, which is given by I squared R, would have been 60 squared times 1 ohm. That is 3600 watts would be lost. And the total power is the product of voltage and current, which is 60 ampere times 120 volt, which is 7200 watts. So we see that half of the power is wasted. So power wasted is 3600 by 7200 times 100. As a percentage, that is 50%. I just want to illustrate the loss of power if it had been stepped up, although it's not asked in the question. If it had been stepped up using a transformer, the secondary current would have been much less, which we can find using this formula, Vp by Vs. It says it stepped up to 4500 volt. So the current in the secondary would be 1.6 ampere only. Therefore, the power wasted is I squared R, which is now 1.6 squared times 1, which is only 2.56 watts. So the percentage power wasted is 2.56 divided by 7200 times 100, which is 0.0355%. Now you see the big difference between the power wasted without step up and with step up. It's considerably smaller, and this is the main advantage of using a transformer for transmission purposes. In the second question, we have a coil of 160 turns, an area 0.20 meter squared, placed with its axis parallel to a magnetic field of 0.40 Tesla. The magnetic field changes from 0.40 Tesla in the x direction to 0.40 in the negative x direction in 2 seconds. Now notice that the change in magnetic field is 0.8 Tesla because its direction changes, and E is d phi by dt according to Faraday's law of electromagnetic induction, and that's for one loop, and because there are 160, you've got to multiply with 160. So you get, divide by the time, of course, which is 2 seconds. And then because what is given is the magnetic field or magnetic flux density. We got to multiply with the area. See, that's the area with which it's multiplied, to change B into phi, because phi is B times the area, which gives 12.8 volt. Okay. And the current in the circuit by Ohm's law is E by R. So that is 0.8 ampere. Now to find the power, we use I squared R. We know the current is 0.8 and the resistance is 16 ohms. So the power generated is 10.24 watts, approximately 10 watts. In this third question, 5 ampere at 110 volt flows in the primary. Assuming 100% efficiency, how many amps at 24 can flow in the secondary? Remember that the power in the primary is equal to the power in the secondary for an ideal transformer. Power is the product of voltage and current. So Vp times Ip is Vs times Is. And that enables us to calculate the secondary current. Which comes out to be 22.92 ampere, approximately 23 ampere. The next question, a transformer has 500 turns in the primary and a 2000 turns secondary. If the current in the secondary is 3, what's the current in the primary? Remember that the ratio of the turns in the primary to the secondary is called the transformer turns ratio. Okay, in this case, the transformer turns ratio is 500 by 2000, which is 1 by 4. Now going back to the problem, Vp by Vs is Is by Ip, which is equal to Np by Ns. So I've put all the three together. We need the second part that's highlighted to find the primary current, which gives 2000 times 3 by 500. It's 12 ampere. In the fifth question, a circular coil of radius 5 centimeter and resistance of 9.2 ohm, is that 0.2 ohms, is placed in a magnetic field perpendicular to the plane of the coil. Okay, remember that if it's perpendicular to the plane of the coil, then the angle here is actually 0 degrees. Because the angle is always taken with respect to the perpendicular down to the plane of the coil, okay, and the magnetic field. So the magnitude of the field changes according to what's given there, 0.5 exponential negative 0.2t, and you got to find the current at 2 seconds. So the idea is to first find the EMF induced using Faraday's law, and then divide that by the resistance. So according to Faraday's law, E is negative d phi by dt, and B is given here. You've got to multiply it with the area to get phi. Okay, so B times A gives you phi, and since the area is constant in this question, A can be taken out. It's dB by dt. Now the area is pi r squared, and d by dt of B, which is that function given, So we got to differentiate that. When you differentiate that, you get 0.5 times negative 0.2 e raised to negative 0.2 t, and at t is equal to 2 seconds, substitute for t as 2 seconds there. So that becomes exponential raised to negative 0.4, and on calculation we get 5.26 times 10 to the negative 4 volts. And therefore the current is that divided by the resistance. Let me include a volt here, okay. That divided by the resistance, which is 2.63 times 10 to the negative 3 ampere, or 2.63 milliampere. In number 6, the output of a generator is 440 volts at 20 ampere. It is to be transmitted on a line with a resistance of 0.6 ohm. To what voltage must the generator be stepped up? Output be stepped up with a transformer if the power loss is not to exceed 0.010%. So the power loss is given here. Power is the product of voltage and current, and it's 440 times 20. That's the output power, which gives 8800, and we take 0.01% of this, which would be 88 watts. And since power wasted is given by I squared R and the resistance is known, we can find I. So I squared is 0.88 divided by the resistance, which is 0.6, and I would be square root of that, which gives 1.2 ampere. So we need a secondary current of 1.2 ampere. We know the current in the primary is 20. We know the voltage is 440 in the primary, so knowing all the other three terms, we can find the secondary voltage. It is 440 times 20 divided by 1.2, and that gives 7300 volt. Now the last question. A constant magnetic field, so B is constant, is applied to a rectangular loop of a particular area, and the area changes to a new value. So using Faraday's law of electromagnetic induction, E is d phi by dt. Once again, phi is B times A, and therefore d phi is BdA by dt. That gives, now look at the change in area. And therefore the induced EMF happens to be 7.9 times 10 to the negative 4 volt. So I hope you understand how these problems have been done. So electromagnetic induction is chiefly governed by Faraday's law, and EMF can be induced either when a coil rotates, the area changes, or the magnetic field changes. Thank you and good luck.